So today we jump onto the MIT integration. We qualify answer 17, problem number 3, which is the definite integral from x equals to 0 to x tending to infinity of the hyperbolic tangent of x over the exponential or e to the power x. So actually a very interesting problem it is, but also a little bit challenging. So let's see how we may be able to solve it. Okay, so 0 to x tending to infinity of the hyperbolic tangent of x over e to the power x. So some definitions. Hyperbolic tangent of x equals to hyperbolic sine of x over the hyperbolic cosine of x. Okay, and we know that the hyperbolic sine of x is simply equal to e to the x plus minus, apologies for that, minus e to the minus x over 2 hyperbolic cosine of x is e to the x plus e to the minus x over 2. So what that means is that hyperbolic tangent of x is equals to ex minus e to the x divided by 2 over divided by 2, which is just simply equals to ex minus ex over ex plus e to the x. And another way we could write it is over e to the x plus and so if you multiply both the numerator and denominator by e to the x, what that becomes is tangent, hyperbolic tangent of x is same as e to the power 2x minus 1 over e to the power 2x plus 1. So using this, our problem is the same as 0 e to the 2x minus 1 over e to the 2x plus 1 times. So that actually is now an interesting problem. We could do a couple of things. I could, since I see e to the x squared plus 1 the denominator, I could substitute directly with tangent theta, and that actually works. Or I could use u. So I think let's go with u. I could say let u be equal to e to the x such that du dx is the same as e to the x, and du can be used to substitute for e to the power x dx, so that 0 to infinity e to the 2x minus 1 over e to the 2x plus 1 is the same as 0 to infinity e to the 2x minus 1 over e to the 2x plus 1 e to the x dx over e to the 2x. We have introduced this e to the x so that we can create e to the 2x in the denominator, and this can be substituted off as du. One other important thing to note is that if we are moving from x to u when x is 0, e to the 0 is 1, and as x tends to infinity, we still have the infinity limit, upper limit. So we have now 1 to infinity, u squared minus 1 over u squared plus 1 du over e squared. So our problem now is which is the same as 1 over u squared plus 1 minus 1 over u squared plus 1 u squared du. So sorry, we made a mistake here and we created 0 there. It's actually 1. So this becomes 1 to infinity, 1 over u squared plus 1. And then we can express this as partial fraction, is same as u squared minus 1 over u squared plus 1. And we can see that this is very similar to this, so we can bunch those together so that to infinity, 1 to infinity, so that we have 2 integral 1 to infinity 1 over u squared plus 1 minus infinity 1 over u squared. This is a very famous integral, 2 arctangent of u minus, this is the same as negative 1 over u 1 to infinity. Okay, so 2 arctangent, let me write it in a way that is allowed and legal. Limit as u tends to infinity of the arctangent of u minus limit as u tends to 1 of the arctangent of u. This minus and minus becomes a plus, so we have a limit as u tends to infinity of 1 over u minus limit as u tends to 1 of 1 over u. So that becomes 2 pi over 2, that's as u tends to infinity, minus pi over 4 as u tends to 1 minus 1 over u, actually this is plus, as u tends to infinity of 1 is 0, as u tends to 1 is 1, so we have 2 pi over 4 minus 1, which is equals to pi over 2 minus 1. So our dear problem, as x when the integral from x goes to 0 to as x tends to infinity of the hyperbolic tangent of x over e to the power x is equals to pi over 2 minus 1. And that is our answer.